So, in the previous lecture we are looking at some of the graph based data structures that can be used to solve the global routing problem. Now, in this lecture, in the present lecture, we shall be looking at some other approaches, namely means bottom up and top down hierarchical approaches, and also some approaches which are based on means optimizing some kind of an objective or cost function. We shall be looking at some of those approaches which are used in practice. Okay. So, broadly speaking, this already we have discussed earlier in detail. Global routing, what does a global router do? It tries to manage the whole routing problem using divide and conquer kind of an approach. It tries to decompose a large routing problem into smaller sub problems which can be solved or handled one at a time. So, global router takes the whole routing problem in its entirety and it breaks it up into smaller sub problems which are then fed to the detailed router one sub problem at a time. For example, a channel routing sub problem. Okay. So, the channel router will look at only that smaller sub problem, and there are very good algorithms available for channel routing. It tries to solve it and then it moves to the next one. So, this makes sense because instead of considering the whole global problem where there can be thousands and thousands of nets and so large areas, so many blocks, so it would be extremely complex to handle. Okay. Fine. So, as I had shown using an example in the last lecture, this can be done by determining rough paths for each net that needs to be connected, which actually means the sequence of the channels or the subregions it needs to go through. Fine. Now, let us come to a discussion on how we can go for global routing in scenarios where our floor plan is given or when our placement is given. Okay. Suppose my floor plan is given, there are some design styles, as I said, where floor planning and placement does not make much difference. So, let us say I have a placement graph available with me, or let us say to start with a floor plan graph. From the floor plan graph, how I can handle the global routing problem. So, let us take an example. For this case I shall show it. So, I am showing the dual graph of the floor plan like this, let us say. So, here I have a floor plan where there are 6 blocks which are placed, and superimposed on the floor plan I am showing the dual graph. So, you recall the definition of a dual graph. Each rectangular region corresponds to a vertex. There will be an edge between two vertex if there is a common boundary between the regions. Between 5 and 1 there is a common boundary, 5 and 6 there is a common boundary, and so on. Okay. Fine. So, this dual graph can be used for global routing. The idea is as follows: for every edge you can define a weight that represents the capacity of the boundary. Like, you see, if the blocks are of shape like this, this is a quite long boundary, which means a number of connections are possible between these two. So, I can have a higher weight for this edge. Similarly, between 1 and 5, the width of this boundary is quite narrow. So, I will have a smaller weight for this boundary. So, the weight of this graph will give you the capacity of the corresponding channel or the boundary, and of course, the edge length will be represented by this Lij. So, both of these are important. Okay. Now, when I talk about global routing, so we have two terminals located in two different blocks. So, we have to find out a path connecting them. Like you see in this graph, suppose I have a pin located in block 5, I have to connect it to a pin which is located in block 3. Now, this graph will be having some weights in each of the edges. Now, higher weight means that is a more preferable path to follow, because that boundary has higher capacity. So, we are trying to find out a path which has the maximum weight. There are many graph algorithms which are existing for that, maximizing the path weight. So, for example, for this problem, maybe you see that your path weight will be this will be your best path, 5 to 4, 4 to 3. So, once you have it, then you have a global routing problem defined. For interconnection, you have to first go through this channel, let us call this C1, then you have to go through this channel, call it C2, and here. So, here every edge essentially indicates a channel. Okay. So, a path between two vertices essentially indicates a sequence of channel it is going or passing through. So, if you have the dual graph corresponding to a floor plan, then directly the path will give you the sequence of channels that you are traversing in order to get the corresponding path. Okay. Now, suppose so we have the placement given to us. So, when we have the placement given to us, then the routing region space is already defined. This is like the channel intersection graph. Okay. So, this is quite similar to the channel intersection graph which we have already said. So, we can use this. So, if we have the placement given to us, but not the if we have the floor plan given, but not the placement, then you can use this approach. But if you have the placement given, then you have a routing graph which is nothing but the channel intersection graph that we have discussed, where the vertices will represent regions which will correspond to channel, edges represent adjacency between channel, or the dual of this. Either way, the dual graph is the channel intersection graph. Okay. Now, you can follow a sequential approach like this. Given a set of nets, well, assume that the nets are all two terminal in nature. In every net, you are trying to connect 2 points, right? 2 points you want to connect, that is a net. So, you can order the nets and handle them sequentially one at a time. The ordering can be based on a number of heuristics like number of terminals. So, a net which contains largest number of terminals can be given higher priority. Okay. Bounding box length, the nets which are farthest away from each other, that I mean the nets which connect points which are farthest from each other, that can also be given priority. And criticality, some nets which are already identified as critical by the user can be given higher priority for interconnection. So, you see there are 3 things: nets that connect more than 2 points, larger number of points can be given priority; nets which connect points which are at longer distances from each other, that can be given priority, or the nets which the user has mentioned or specified as critical, which would determine the overall performance of the system, that can also be given priority, so that the best path can be found for them. For the others, maybe you will be finding a roundabout path, not so good. Okay, that can be acceptable. So, the sequential approaches use typically variations of maze running or line search methods, and there is another, you see, means I will just mention this, there is a very commonly used method for rip up and reroute if something goes wrong. You see, what will happen? Typically, the situation is like that. Say you take a routing problem, try to solve it using the methods that we have discussed, global routing followed by detailed routing. At the end, you may find that there are some nets, a set of nets, which you are still not able to route. So, for those, as the last resort you can use the maze or area routing algorithm to find a path if from anywhere it is existing, because when you are using or into the detailed routing phase, you are only considering one channel at a time, you are not looking at the global scenario anymore. But if you see that there are 2 points which are still to be connected, you first try any of the maze routing algorithm to see that whether you are able to find a path. If so, fine. Otherwise, people typically use, well, it is a last resort, it is called rip up and reroute. Rip up means, you see, many of the routing decisions that you take are based on some heuristics, which means if you run it again, maybe you will be getting a different solution. Rip up means some regions where you find that there is some congestion, you withdraw, means all the nets which have been routed and again redo it. Maybe the next time you do it, you will be coming up with a better solution, you will be coming up with a different solution which can be better, which may be able to accommodate this new connection as well. So, rip up and heuristic works pretty well typically, and it is a favorite for many designers when they are into the last phases of the physical design. Okay. Fine. Well, of course, you can go for the hierarchical approaches. So, here what we do, here we use the hierarchy of the routing graph. So, again this is a divide and conquer kind of an approach. We decompose a large routing problem into smaller sub problems which can be solved independently. And once you solve the smaller sub problems independently, you will have to combine them together again. So, you combine them together to get the overall solution, right. So, I shall show an example. So, you define something like a cut tree which is quite similar to the tree that we had discussed when we were talking about the partitioning problem, that we define some kind of a partitioning tree and you can cut it, get some partition, something similar to that. So, the cut tree is defined in such a way that every interior node of the cut tree represents a global routing problem, and each of these global routing problem can be solved independently. Now, these smaller nodes indicate global routing problem which is smaller in size. You see, we shall see later that how the routing problem can be translated into an integer programming problem. See, integer programming problem, the advantage is that you are mapping it into an optimization problem which you are solving using some available tool, solver tool. Now, the advantage is that once you get a solution, you are guaranteed to get the best solution, but the problem is that you cannot use it to solve large problem instances. You can use it only for smaller sub problems, so that when you are using a divide and conquer kind of an approach, it means it actually makes sense. When you have a smaller sub problem, you can use integer programming to solve it optimally, and when you have many such sub problems which are solved, you combine them together to get the solution of the total problem. Okay. Fine. So, a very rough idea behind it. Let us say initially the total routing problem, they can be divided up into 4 sub problems with respect to the regions on the layout surface. So, this is similar to partitioning. So, in this method, as if we are using means partitioning and routing in a hand in hand way. So, 1, 3, 2, 4, then again 1 in the next level can be mapped to a block A, 3 can be mapped to 2 blocks D and E, 2 can be mapped to B and C, and 4 can be mapped to F. So, this can be represented by a graph like this, where each of these nodes represent individual routing problems. Like for example, this B is a region containing many blocks. You solve the routing problem here, solve the routing problem here, combine this B and C, you have solved 2. Similarly, you combine D and E, you have solved 3. in this way you go in a hierarchical fashion and you can solve the sub problems. So, the top down approach says, so this is the cut tree which is called, you can cut it any places. So, the leaves I am assuming is at level h and the root is at level 1. So, you traverse the tree from top to down level by level. So, it is like this, this is a top level view, you go down you get a more detailed view. If you want to further break this, you go to a more detailed level, this is top down. So, the problem instance at level I at every stage you can solve using an integer programming problem, okay, because they will be manageable and smaller in size. So, without going into the detail, roughly this is the stepwise procedure, that you compute solution for the routing problem I1 for the trees starting from the root 2 to h, the leaf nodes. For all nodes at level I plus 1, you compute the smaller sub problems using some method like integer programming, then combine all the solutions. So, you do it for all the level by level, you go on doing this, simple. So, conceptually this is simple. Bottom up is the different. Bottom up you are going from the bottom to the top. That means, the routing problem associated with each branch of the cut tree is solved. Then you combine them to form a node at the higher level, then you move to the higher level. But the problem is that, means as compared to the previous approach top down, where you started with a global view of the problem, you try to divide it up into partitions and try to solve it. But here you are looking at the smaller sub problems and try to combine them together, but you do not know what your final routing problem will look like. So, you will get the global picture only much later, okay. And actually, so in practice what is done, some mixture of top down and bottom up can be used for handling large problems, okay. So, again this is the algorithm for bottom up. So, for all nodes at the bottom level, you compute the solutions by combining the solution of the children nodes. You go on repeating this from the leaf node down to the root node, bottom up fashion, okay. This is just the conceptual steps, okay. Now, in this kind of hierarchical approaches, one thing I mentioned is that at every stage you have a routing sub problem and you are trying to optimally solve it using some kind of integer linear program. You map it to an integer programming problem and you use an integer programming solver. So, many such solvers are available, you can use it to get a good solution. And as I had said that you can use this kind of solvers to get solution for small to moderate size problems, but not for large problems, because the time complexity increases quite rapidly. So, the concurrent routing of the nets. So, here what we are saying is that we are not considering one net at a time, but we are considering several nets together. Now, for this kind of a general routing problem, like see, I am just repeating. So, when I am considering a small problem instance, so that problem instance will not contain one net, but maybe there are 10 nets to be connected. So, I consider this whole problem of connecting 10 nets together and use integer programming to get a solution. But our other solutions which we have discussed earlier, they typically take one net at a time and try to handle the routing problem and solve it incrementally one at a time. But here we have one method where we can take a problem where multiple nets, the routing issue of them can be handled in a concurrent fashion, okay. So, global routing problem in this case can be formulated as a 0-1 integer programming problem. 0-1 means the variables take on the values 0 and 1 and the solver tries to solve for all the variables. Now, the idea is as follows: the layout is modeled as a grid graph. This we can possibly afford because our sub problem is not very large. There are n number of vertices which represent the grid cells. There are m number of edges which indicate the adjacency between the vertices, and the edge weights, as I mentioned earlier in the data structures, represent the capacity of the boundary. Okay. Now, let us see how integer linear programming formulation can be done. So, it is in fact it is quite straightforward. We do it in this way. Suppose I have a net I, let us take an example. Suppose in a problem instance, so I have a net I where there are several points. So, now we look at several different ways of connecting them. Well, I am just showing several alternatives. So, one way of connecting them may be like this. This may be one possible connection. Say another way of connecting may be like this. Say another way of connection may be like this. So, for any net Ni, there can be several alternatives. Typically, you know, when you lay out the wires, you just model them as means Steiner trees. So, you can say there can be many Steiner trees corresponding to every net that you are going to lay out. This is something you have to evaluate. So, here we are assuming that for each net Ni, there are some Ni possible Steiner trees. So, there are algorithms to approximately determine the possible Steiner trees for nets. So, you use one of those algorithms and let the Steiner trees be denoted by T1i, T2i up to Tni I. Well, now out of these Ni Steiner trees, you will have to select one of them to route the net. Okay. For a particular net, you have to use only one way of connecting them, not more than one way. Okay. So, this you specify like this: you use a variable xij, where xij will be 1 if net I is routed using tree Tji and 0 for all other j values. So, out of the possible Ni values or Ni trees, only one of them will be having the value 1, for all others it means 0. This means that I am using the jth Steiner tree for connecting net n. This is one, and just to make sure that I have selected this 1 for only one j value, for all others I have made 0, I also add a constraint that sigma of xij should be 1. That means a single 1 followed by all other 0. That means one Steiner tree should be selected for a net. So, we can represent the constraint like this. Okay. Now, suppose the grid graph has m edges and there are capital T trees for all the nets. So, Ni is the number of trees for net I. So, there are so many nets, I am saying that we want to handle concurrently. So, sigma of Ni will be the set of Steiner trees for all the nets under consideration. Okay. So, capital T will indicate the total number of such trees. So, the routing problem we can define as follows: we define a matrix capital A which will have dimension m cross T. So, m is the number of edges, that many rows, and number of trees as the column, and the coefficient will be 1 if a edge belongs to a particular tree and 0 otherwise. So, this will tell you that which tree is using which edges. So, you appropriately set the entries of this matrix to 1, okay, and each boundary arc will be having a capacity C I. You ensure that the capacity does not exceed C I. What I am doing? This A I P multiplied by x, mean x is which, you recall x is this matrix, which net you are using. So, only for one of them it will be 1, for rest there will be zeros. So, you see total number of edges that we are taking, that should not be crossing the capacity. Okay. This is actually for all the nets, not for one, for all the nets. You see that the total capacity of the link I should not be crossed, and if each T I you assign a cost G I j, then the objective function may be to minimize the sum of the weighted cost for all the trees. So, this will be our overall integer programming formulation. So, which can be summarized as follows: minimize this objective function subject to this condition which says only one of the Steiner trees for each net we are choosing. This says that for each boundary C I, each boundary I, the number of nets crossing should not exceed C I, and x k j, these are all binary values. So, if you solve this problem, you will get values for the variables x I j, a I p and so on. This will be the output of the integer programming IP solver. IP solver will give you the values of the variables that minimizes the objective function, which is nothing but the solution that you want. You will get the solution that for every net which Steiner tree you are selecting, and for each Steiner tree which edges you are using. Okay. So, the matrix is A, and that x will give you that information. So, this is just one thing that using integer programming you can get the best solution for a routing sub problems, if provided the number of nets and the size of the nets is not very large, then you can use this to get an optimum solution. Now, of course, there is another important issue which we will be dealing with in detail later when we talk about performance driven issues like timing and delays. See, with the advent of the deep submicron technology, as the devices or the transistors are getting smaller and smaller, the delay of the interconnection is starting to dominate. So, earlier the gate delays were higher, the interconnection delays were less, smaller, but now it is becoming the other way around. The interconnection delay is becoming as important as the gates, and sometimes it is also dominating. Okay. So, this crosstalk noise issues, we shall also be handling this. So, increasing proximity between the devices because of the small sizes and increased density. So, this has also resulted in increase in crosstalk noise issues. So, modern day routers should also consider the crosstalk noise. So, we shall see later that we can introduce buffers to reduce noise across long segments. Wire sizing, some wires can be made more wider as compared to the others, and topology generation is something that also which we shall be looking at. So, with this we come to the end of this lecture. Now, in the next lecture which we shall be starting next week, we shall be first looking at the detailed routing sub problems and some of the techniques which are used there, followed by we shall be moving into the timing related issues. We shall be starting with some discussions on clocking and how we can route the clock nets and so on, after which we shall be going into some other timing related issues like static timing analysis, crosstalks, etc. Thank you.